Okay, welcome to lecture here. We're continuing on with chapter 12, I think it is, and kinetics. Perfect. And again, make sure you put here in that role. Perfect. Move a couple of things around here. Okay, so last week we were getting into kinetics, obviously, and we sort of finished up talking about this idea of temperature and energy and the rate of reaction. Remember that typically, if you increase the temperature, as we sort of talked about, and we'll talk about again here, the rate of the reaction will increase. Um, if you lower the temperature, typically again, the rate will sort of slow down. And really, the reason for that is what we sort of were talking about at the very end last time, which is what we see here on the screen, and with some energy diagrams. And these are energy diagrams. Um, one's an exothermic reaction, one's an endothermic reaction. Exothermic, as we've talked about, is when heat and energy is released, and endothermic is when heat and energy is absorbed. And in the case of an exothermic, as you can see on the left-hand side there, typically the way you can recognize that is your reactants there are higher in energy than your products. So essentially, it's got to give away some of that energy to come down to our products. And opposite of that is endothermic, where we absorb heat and energy. So typically, we could see that where our reactants are lower in energy than our products. So to sort of get to the top there, where our products are in terms of energy, energy has to be put in or absorbed by the system. Now, when we do get to the very top of this hill, and there's a hill in both of them that we talked about last time, and that's the hill between where the reactants are in terms of energy and where they're starting, to the top of the hill, where we do have our transition state. That's what is referred to as the activation energy. And the activation energy is the minimum amount of energy that's required for a reaction basically to take place. Is again sort of thought of, as you can kind of see in this picture, as the hill that basically the reactant has to climb to get to the other side to form your products. And remember, in a chemical reaction, the only thing that happens is everybody pretty much breaks apart their bonds, and then they form new bonds on the product side, new compounds and things of that nature there on our product side. Now, when we get to the very, very top of the hill, as we talked about, that is where we refer to again as a transition state. And usually, what you have at the very top of the hill is a sort of a species where it is sort of partially broken some of those bonds as it's sort of making its way to the product side, and there's partially making some new bonds as it also is going to the product side to make new products. So you have this guy that's really, really high in energy. And as we talked about last time, if you are really high in energy, that's usually not a very stable sort of situation to be in. Most things like to be in the lower state of energy. And you can see in terms of these diagrams that that transition state is really the highest point in terms of energy and sort of the most unstable, I guess is a way to wording that. And that guy that you have up there again, which is referred to as a activated complex or transition state complex, doesn't really hang around a very long time because again, it's got those partially made bonds, partially broken bonds, and will very quickly go down to our product side. Clearly, in terms of the rate of the reaction, this hill that the reactants has to climb to get to the other side obviously will have a drastic effect on sort of the rate of the reaction. Obviously, just logically thinking about it, if it's a larger hill that the reactants has to climb to get to the other side, then you would expect the rate probably to be a lot slower than if you had a much smaller hill to climb to the other side. You would expect it to be a lot faster, the rate of that particular reaction. Activation energy is always positive, as you can see here. It's an endothermic type of situation, so it always should be a positive number. Again, is being put in to get to the other side. So when we do calculate things like activation energy, should typically be a positive value. relationship in terms of energy, just a reminder, again, as you learned probably in Chem 50, delta H, which is our enthalpy. That's the heat of a reaction. And that heat of a reaction is either positive or negative, that delta H value. And if it's negative, it basically represents a exothermic reaction. If it's positive, it represents an endothermic reaction. So a lot of times you are just given sort of a delta H for a reaction, and from that you can determine whether or not it is exothermic or endothermic based solely on the enthalpy value, not truly the value, but whether or not it's positive or negative will allow you to determine if it is exothermic or endothermic. Any questions on that stuff we sort of left off on last time? Okay, so what we are going to talk about again now is really the effect of sort of temperature on rate, the rate constant, and so forth. So let's take a look at that. So the effect of temperature on the rate is sometimes what is referred to as the Arrhenius sort of relationship. And here's one version of it, really a version that we don't use a lot, but K, which is the rate constant here, equals A. A is what is known as a frequency factor, as you can see down there. This again is our rate constant, which it kind of tells us, you know, how fast or slow is progressing. E is sort of that inverse of the natural log E, so that's that. E of A is our activation energy. R is the gas constant, but it's not, again, the one that we use in the gas law. It's the one that involves energy, so it is that 8.314 version of it is our gas guy. And T is our temperature that does need to be in Kelvin. Now, this is one version of it, and basically the frequency factor, as we will talk about, is really sort of the proportion of molecules that does have sort of a sufficient amount of energy to get up and over to the other side. So that is sort of what the frequency factor is. There's only a certain amount of molecules that can get up and over to the product side. And also something we talked about, I think, last time as well. Just because there is a collision, it doesn't necessarily mean that products will be formed. So just because reactants do come together and sort of collide with each other, it doesn't always necessarily guarantee that products will be formed. They do have to sort of hit each other in the right sort of orientation, and they do have to hit each other with that minimum amount of energy, which again is that sort of activation energy to get to the other side. And that's what we see here again. Basically what's happening as this reaction progresses, these reactants need to break apart, and again climbing this hill till where they're partially broken, partially made, and then kind of quickly come down to the other side. Here we would be able to predict that this is an exothermic reaction. Again, our energy of our reactants are higher than our products. So again, in order to get down to the other side, energy would have to be given off in this particular reaction, making it exothermic. So there is that energy barrier, as we talked about, which is the activation energy. Not good colors choice there. I can barely see on mine, but hopefully you can. The activation energy, as I mentioned, is that minimum amount of energy that's needed to convert the reactions into the activated complex or transition state. Remember that activated complex or transition state is the top of the hill, the highest point in terms of energy. And again, that's what that activated complex is. The activated complex, as it shows there, is, as we've been talking about, something that's very high in energy, really sort of unstable because of that. And partially it's really unstable and high in energy because it has those partial bonds, those partially made bonds, partially broken bonds. You know, you could almost think of it as sort of a transition point of going from reactants to products as it sort of transitions from one to the next. And that's sort of the middle part there, that intermediate that kind of gets you to the other side. Now, this Arrhenius equation, if we sort of look at a graph here, and by the way, here's just a graphical representation of sort of what's happening here. This guy is basically rearranging the carbon to the nitrogen procedure, although it may look the same. We're rearranging bonds as it goes through here. And so kind of a step-by-step. So what we're talking about, for this reaction to occur, you got to start breaking that bond between the nitrogen and the carbon, and starting to form a new bond between the nitrogen, the carbon, and the nitrogen, carbon and the carbon as it goes through here. And that's sort of happening here. So here's our original guy. You can start to see it starting to sort of break its bonds as it's working its way up the activation energy there. Again, when it gets to that very top, it's got that partially broken bonds. It's starting to make the bond now with the carbon coming in, and then going to work its way back down to the end. And again, that difference really between reactants and products in terms of energy is where we get our delta H for the reaction. If you remember, when you calculate delta H in Chem 50, it was products minus reactants, and that's the whole idea here. This is our products minus our reactants, sort of the difference in energy from where we started and where we ended up gives us our delta H for that reaction. And again, in this case, we would expect it to be a negative value as our reactants are higher in energy than our products. But again, as it starts moving up the hill, starting to break some of those bonds, still together here, but at this point going to start to make some new bonds here, kind of fully break apart from the nitrogen as it comes down that hill to the other side. Now, when we look at Arrhenius equation here, here's a couple of things on this graph. Here we can see what we've been talking about. We do see a rise in the rate constant as it goes upwards there. And grab this real quick. So at lower temperature here, we have a much lower rate constant, or rate for the reaction, and we can see a gradual increase in the rate as we increase the temperature. And again, here, the idea is when we do increase the temperature, everybody gains more energy. By gaining that more energy, it's going to allow them to get up and over that hill, basically to the other side a lot easier. There's a greater proportion of molecules that essentially have the correct amount of energy to do that. And that's going to be very helpful in increasing the rate of a reaction. Now, when we look at the Arrhenius equation, this is not necessarily usually the version of it that we use. If we go through there and sort of take a natural log of everybody, this equation here is typically the equation of the formula that we commonly use. And we commonly use this guy for sort of graphing purposes. So when you're sort of looking at the relationship between the rate constant and temperature, we oftentimes will use this version of the equation here to do that. And the reason for that is this is the version of it in the form of a straight line. So if you use this guy here, this is your y is equal to mx plus b. So this is the form of this in a straight line. It's going to give you a nice linear relationship. That is not the graph here. We'll see the graph in just a second. But what we basically do graph is, as you can see here, on the y would go the natural log. So typically that graph, as we will see, will have the natural log of k on there. And x is equal to 1 over the temperature in Kelvin. And what this usually yields you is a nice kind of straight line that has sort of a negative slope in most cases. And that's good because if we take the slope of this line, that is equal to minus E of A over R. So this is a very convenient way to sort of graphically determine something like the activation energy for a reaction by making this graph. That's because if we take the slope, R is our constant, R is our 8.314 version, and M we would get from the graph. And because this line typically is negative, the slope value will be negative. That negative and this negative will turn our activation energy into a positive value. So again, the activation energy is typically positive, And that negative there, again, is to make sure that you do end up that way when you make this sort of Arrhenius glass. So that's an important equation to know. Also, in terms of units, we should also think about a couple of things. But typically speaking, we're going to see this equation and another equation, and just this part of the formula here, where we have the activation energy and we have the gas constant. And I'll be honest with you, usually when people calculate the activation energy, it is usually in kilojoules, and R is usually in joules. So mathematically speaking, not necessarily the graphical part of it, but we'll see it a little bit later in just a second. These two guys in this sort of formula here, you do want to definitely watch the units on it, because like I said, usually activation energy is given to you in kilojoules, and usually R is obviously in joules. So you will be off by a factor of 1,000 if you don't convert one of those numbers. So usually this comes into play when we sort of do the non-graphical version of it, which you'll see in a second, but it's something to keep in mind. Those guys typically do have different units in terms of their prefix. One, again, being kilo, which is our activation energy, and the R value being typically just joules. And here is an example of a graph like that. So this is an Arrhenius plot here. And as you can see, you do get a very nice relationship, a nice linear relationship, again, because this is y is equal to mx plus b, this nice linear line where, again, if you took the slope of it, equals minus e of a over r. Again, a very good and sort of convenient way to graphically figure out the activation energy for something, our reaction. And we talked about some of this stuff in here, but again, this sort of version here, this exponential factors basically represents sort of that fraction of molecules that does have enough energy to get up and over to the other side. And as we talked about in terms of relationship to the rate, obviously, the larger the hill in a sort of room temperature sort of situation or normal temperature situation, there's obviously going to be fewer molecules that have enough energy to get up and over to the other side. That amount of molecules increases as you increase the temperature. Everybody gets more energy when you increase the temperature. They have a greater number of molecules that can hop to the other side. And obviously the opposite is true. You know, if you took a reaction and you threw it on ice and really cooled it down, you're removing a lot of energy. So now the normal amount of guys that normally would have enough energy to get to the other side, there's going to be less of them that have enough energy to get to the other side. And again, that's why we typically see the rate of a reaction when we decrease the temperature obviously slow down. Because of that, you now have really removed out a lot of energy, and you have a very, very smaller amount of guys that have enough energy to get to the other side. And that obviously is what we've been talking about. If you increase the temperature, you're increasing that energy. And we can see here graphically of that, we have basically the same reaction, and it's at two different temperatures. The red line there is temperature 2. The blue line is temperature 1. And temperature 2 is a greater temperature or a higher temperature than temperature 1. And what we see is where we hit the activation energy sort of hill, when we look at our temperature 2 situation, this amount of guys have enough energy basically to get up and over on the other side. While if we look at temperature 1, which is a lower temperature, really only about from here down, the red part there would be the amount of molecules that have sufficient energy to really get that reaction going to the other side. And obviously you can see it's much less proportional molecules at that lower temperature than at the higher temperature. And if you just look at one graph, just in general here, again, if we sort of lower the temperature coming back, this way, we're getting much smaller amount even still that obviously hasn't got to the part where it needs in terms of energy. So lowering the temperature, raising the temperature, obviously has a drastic effect on the rate of the reaction by really either adding or taking away energy when we look at it. So here's this equation in case you missed it the first 7 times we saw it in the last 3 slides. Still the same stuff. And again, this is typically the version of the equation that we use really for graphical sort of purposes. Works really well for a graph. And again, if you are given sort of the information here to sort of graphically make this, which you may be in some book problems, again, typically what you will be given in a table is a bunch of K values, so a bunch of rate constants, and you'll be given the temperature. Temperature could be in Celsius, could be in Kelvin. If it's in Celsius, you do need to convert it to Kelvin. And then what you need to do with each of those values in the table is essentially take the natural log of the K values and take 1 over the temperature values in Kelvin. And again, that is what you would plot, natural log of K on the Y, 1 over T on the X. And again, you could use all that stuff to figure out, again, the activation energy. You could also use this guy here to figure out the frequency factor, which again is that proportional molecules that can get to the other side. And again, in terms of the formula, Y equals mx plus b. So b is the y-intercept. So you could use the y-intercept basically to figure out the frequency factor as well in a particular reaction. So let's take a look at one here, a sort of problem like you would use this graphical sort of approach to it. If we want to determine the activation energy and the frequency factor for this following reaction, again, in a problem like this, you would be given a table such as this. In this particular case, they were nice enough. They did convert our temperatures to Kelvin. If they didn't convert our temperatures to Kelvin, you would need to do that. And again, we want to think about the equation that we just saw, the natural log of K equals minus E of A over R, 1 over T plus the natural log of A over here. So basically for everybody here in terms of our temperatures, because they're already in Kelvin, we do need to take 1 over T. And that is essentially what we would plot. For our K's here, we do need to take the natural log of K. And that's what we would plot on the X. We would do sort of an XY scatter plot, do a best fit line later in regression. Again, if you're using Excel or something like that, add a trend line, and you would get the equation for it, and that will allow you to sort of figure out what is going on. So if you did that graph, you get something such as this here. And again, you can see it's a very linear line, as we talked about, sort of this negative slope line happening. And this would be, again, the equation that you could pull from something like Excel. If you graphed it, you could do it by hand. Probably better to use some type of program, I'm assuming, than to try to hand graph something like this. So using this, since it's graphed for you, you have the equation. Why don't you take a couple minutes here, and why don't you actually calculate what it is asking you to calculate? So why don't you calculate the activation energy? So what is the E of A for this reaction, and what is the frequency factor for this guy as well, based on this graph? So take a minute or two, and then we will talk about it. Okay, so let's take a look here. So again, this is again more of a graphical way of sort of solving for these things. And obviously to do this, you would need to make a graph. Um, so they made the graph for us. They actually gave us the equation, which is essentially what we need. So we're going to take a look at a couple of things here. First off, we're looking for E of A, which is our activation energy. And remember that from this, the slope of the line is equal to minus E of A over R. So we could use that relationship to figure out our activation energy. That means that our activation energy would equal minus R times the slope. So again, in this formula here, the slope is this number here. And that would mean that we would have minus 8.314, which is our gas constant, times our slope, which was given to us with the equation there. And that is going to give us we got 8.314 times 1.12 to the fourth gives us something like, if we just multiply it, 93116.8. Those would be units of joules, really, joules per mole, really, because there's actually a Kelvin over here that cancels. But usually, again, it's given in kilojoules. So if we divide it by 1,000, 93.1 kilojoules per mole would be our activation energy. Again, as we talked about, it is usually a positive number. That is why the negative is here, and that negative there from the slope will make it into a positive number like we see here. Any questions on the activation energy calculation there? Again, it's pretty straightforward. You essentially just take the slope, times it by 8.314, and you pretty much have your activation energy in joules. And again, you might just have to usually do a conversion to kilojoules because that is commonly what we got going on. Now, in terms of our frequency factor, which is A, the natural log of A is equal to our y-intercept. So in this particular case, our y-intercept is this guy, which is B, from our equation. That means that the natural log of A is equal to 26.8. That means to get rid of it, we're going to take the E of both sides here. When we do that, that cancels. We get A is equal to E of the 26.8, going to give us an A value of 4.36 times 10 to 11. Now, you may be wondering maybe what the units are, and the units here are actually going to be reciprocal seconds and molarity, reciprocal molarity seconds. It is the same units that we see for our K, basically. So basically the y-intercept, right, is very badly drawn where it crosses the y. So the y is the natural log of K. When we take the E of that in that calculation, we're back to just K. And that's why the units end up being the same as the rate constant, because basically the y-intercept is the natural log of K. And in that mathematical move, when we take the E of it, it just becomes K, and the units basically default back to the same as the rate constant. And again, if you look back on the table there, those were the units that we associate with the rate constant. So easy way to remember that is usually if you solve for the frequency factor, usually will have the same units as sort of the rate constant. And again, mathematically, it's because of right here when we kind of do this move. It kind of takes us back to the units of the rate constant. Any questions on graphically how to determine those two things? So again, this is one way that you could commonly determine these things. Another way is people don't really like to make graphs all the time. So sort of a mathematical approach is another way that we can sort of calculate these things. We calculate rate constants, activation energy, temperatures, if we have basically 2 points or two pieces of information. And that's why it's sometimes referred to sort of the mathematical approach to the Arrhenius equation is this one here, sometimes referred to as the 2-point form, which basically means you have enough information basically almost for 2 points along that line. And you can sort of mathematically solve for it. And one version of this equation, and by the way, if you look it up somewhere, you may see some different versions of this equation. And it's mainly on the right-hand side here. Sometimes they'll combine the denominator there and have T1 times T2. Sometimes they'll factor out the negative to the outside, and then these two guys will switch. So there's probably like 3 different versions of this equation that you sometimes see. I believe this is the version that is used a lot in our books that we typically get here. But again, there are some different sort of versions of it. They all should give you the same answer as long as it's a legitimate version. So on the left there, we have the natural log of K2 over K1. So that's basically 2 rate constants for 2 different conditions or temperatures, equals E of A, which is our activation energy, R, which is our gas constant. Again, here still the 8.314 version of it. So again, this is the same R we've been using, 8.314. These are our temperatures, temperature 1 and temperature 2. They do need to be in Kelvin. Make sure pretty much like everything in chemistry, right, needs to be in Kelvin. And this is K2 and K1. Clearly the K value and the T value, these two guys go together. And obviously the T1 goes with the K1 in terms of its temperature. This is definitely the one where you do want to watch units. So as we were just talking about here, typically our activation energy is in kilojoules. So again, if you use kilojoules on top, joules on the bottom, you are going to be off by a factor of 1,000. So you want to definitely watch that guy, especially with this version of the equation. But this allows you to solve for a variety of things. You can do, you figure out a rate constant if you change the temperature, if you know the first temperature and first rate constant. Vice versa, you can figure out the rate constants as temperature changes. If you can figure out the temperature to get somebody to a new rate constant, you can also figure out obviously the activation energy and so forth. So this is probably in most cases how you'll probably use the Arrhenius equation is sort of this plug and chug sort of version of it. But again, the graphical version is also used a good amount of times. So why don't you try one here? We're looking for the activation energy under these conditions. We have a rate constant 2.57 at 701 and 567 at 895. What is the activation energy in kilojoules per mole? So see what you come up with. We'll talk about it. Take a couple minutes here. Okay, so let's take a look and see how we're doing. So if we pull out the information, we got a couple of rate constants. We got some temperatures. So we could call K1 here 2.57. That goes with our T1, which is 701. Our K2, 567. And our T2 of 895. So again, obviously we have 2 points here. We're looking for activation energy, so we do want to use our Arrhenius equation here, K2 over K1 equals E of A over R. Again, no negative in this version of it, just so you can see here. 1 over T1 minus 1 over T2. Now, sometimes people ask, how do you know which one is K1 and K2? Truthfully, most people just go in the order you see it in the problem. And in reality, it doesn't matter as long as you keep the correct K value and temperature value together. So what I mean for that is, for example, I made those both ones. I could have done them both as twos. Mathematically, it all should come out the same, really, regardless sort of which one you label as 1 and 2, as long as, you keep sort of the data together that goes together. So plugging in here, we got our natural log of our K2, which would be 567 over 2.57 equals E of A, which is what we're looking for, 8.314, which is our gas constant. 1 over our first temperature, it is already in Kelvin, so we don't need to add 273 to it, minus 1 over our second temperature of 895, also in Kelvin there, so we don't have to worry about it. So we want to do some cleaning up here in terms of the math. Also, something sometimes people mess up on is you actually want to divide first, so 567 divided by 2.57, and then take the natural log of it. Sometimes people want to take the natural log of everybody and then divide and get sort of the wrong answer. So 5 point, looks like 39645. We'll take it to a bunch of units here. 8.314. I'm also going to clean up what I got going on in here. So that was 1 divided by 701 minus 1 divided by 895. Looks like it gets me something like 0.000309215. I'm then going to divide that to the other side. So I'm going to take that and divide it to the other side. So our 5.396 divided by our 0.000309 going to give us something like 17452.107 equals E of A over 8.314. Lastly, here I'm going to multiply the 8.314 to the other side. So when I multiply the 8.314 to the other side, I end up with an E of A that is 145096. The units here, if you kept track of everything, is going to be joules. Kelvin will cancel, and really our, joules per mole or kilojoules per mole is basically what our units will be. This is joules per mole, and again, usually in kilojoules is what we're looking at, so 145 kilojoules per mole. Again, a positive number here, and what we would expect. Sure, the last part, like here, this part. The 1 over this part here. So yeah, so you just, so the part in the parentheses is you take 1 divided by 701, hit equals, minus 1 divided by 895. If you're going to put it on your calculator, probably do some parentheses, 1 over 701, hit equals, then hit the subtract button, little parentheses again, 1 over 895, or you could use your -1 button and hit equals. And if you do that, you should end up with this number here, the 0.003092. And then we divided that to the other side. So we essentially took, I just got to move a couple of things out of my way here. So after we got that number, we divided basically 5.39645 divided by 0.000392. 309, and that got us to here. Other questions on that? You're welcome. Any other questions on that particular one? So again, this is sort of a mathematical approach to temperature, rate constant, and again, probably more common way that you will sort of use this equation. We also see, what we were talking about as well in terms of temperature and the rate constant, for example, at 701 Kelvin, our rate constant was 2.57. In this particular reaction, we bump it up to 895. We see a big jump in the rate constant. So again, at that higher temperature, we have more molecules that have enough energy to get to the other side. The result of that is a higher rate constant or rate for the reaction. As you can see just by looking at the numbers, 2.5 to 567. So a pretty big jump in terms of how fast the reaction would take place. Other questions on that there? Why don't you try another one here just to make sure? Here's some hints. So it's often said if you raise the temperature by 10 degrees Celsius, the rate will double. So calculate the activation energy for such a reaction, and there's some hints to help you out and see what you come up with. that up so you can actually hear me. All right, let's take a look and see how we're doing. So we got T1 and T2. So we're really doing sort of a 10-degree difference, and in reality, you can choose sort of any 10 degrees, but we'll go with what they had, which was T1 is equal to 300 Kelvin. T2 was equal to 310 Kelvin. And they said that basically K2 was twice as fast as K1, or the rate doubled. So that basically means that K2 is equal to 2 times K1. So it's basically what this means. This is like the rate doubled, is basically why we're taking 2 times our original rate. Again, we increase the temperature, the rate basically doubled. So that's why we get to that. So using our formula here, natural log of K2 K1 equals E of A over R 1 over T1 minus 1 over T2. Putting that in there gives us really the natural log of 2 on this side. And the way you get the natural log of 2 is it's the natural log of K2, which is 2 times K1 divided by K1. Although we don't know these numbers, they do cancel. And that leaves us the natural log of 2 on the left-hand side. And that's how we get to the natural log of 2. E of A is what we're looking for. R's are constant. And our temperature, 1 over 300 Kelvin minus 1 over 310 Kelvin. Again, if we sort of clean up some stuff here, natural log of 2 is 0.693. E of A over 8.314. And again, I'm just going to clean up this part here and get a number. So that's going to be 1 divided by 300. I would hit equals minus parentheses 1 divided by 310. Close the parentheses gives us 0.000107.5 and some more. Just like last time, I'm going to divide that to the other side. That's going to cancel. And that'll get me dividing that to the other side there. Looks like 6446.26, just to take it to a couple of digits. E of A over 8.314. Again, we're going to multiply the 8.314 to the other side. And that is going to give me an E of A of 53594 joules per mole. Remember, joules come from here. Kelvin cancels here, leaves us joules per mole. And again, if we go to our normal sort of kilojoules for that, gives us what we got there, 53.6. It looks like a round on that. So 53.6 kilojoules per mole. Again, positive number here. And you could have chose, like I said, any sort of 10-degree difference, as long as you kept it sort of normal temperature, if you will. And you'll get somewhere around that. You'll get a little bit slightly different if you chose, say, 310, 320 or something like that. But in that sort of ballpark, you'll get somewhere in this number. Question on this calculation, where the numbers came from, why we did any of it. You obviously need to know that equation. You need to be able to use that equation to solve for a variety of things. Obviously, you can see in this equation, you can solve for any of the K values, activation energy, or any of the temperatures if you're given enough information. And probably in most cases, this is probably the version that you'll use. Again, you still need to know how to do the graphical version of it and sort of get the information from that. My guess is the graph would be provided for you in the other case, and the equation would be provided for you, and you just need to know how to kind of get the information. This one, obviously, you need to know how to plug it in and solve for it. Any questions on temperature, the Arrhenius equation, or how to use it? Okay. So we're going to sort of finish up this chapter talking about really what is referred to as mechanisms and sort of how reactions basically take place. And, it's sort of idea of collision theory that we've been talking about. And again, this is just to illustrate that point that we mentioned a couple of times already, that although you really do need sort of two things to occur for a products to be made and really a reaction to take place, you do need a sort of a collision. So you do need the reactants basically to come in contact with each other. But again, they do need to come in contact with each other in sort of the right area and with sufficient energy. So those are sort of the two sort of things. So in the sort of top version of it, you can see that the purple circle there, which represents the iodine, is coming straight at the potassium. And when they collide in that manner, we do get products formed. We get the potassium iodide and the CH3, the methyl group coming off. But if we have the same two guys colliding where sort of the potassium collides with the carbon, we actually will not get products formed. And again, that sort of collision between the potassium and the carbon won't result in any sort of product formation, as opposed to here where there is going to be some attraction because it wants some of those electrons and negatively charged, sort of positively charged, going to be some donation happening of electrons there. So they're attracted to each other and will allow that reaction basically to take place. Another important part about reactions is what is referred to as reaction mechanisms. And an important thing to keep in mind is sort of this idea that not all reactions really do occur sort of in a one-step fashion. So oftentimes we think about reactions as, oh yeah, it just goes directly from reactants to products. You know, it's just like a one-step situation when how a reaction takes place. And that is not always the case. And one really good example of that you should have some experience with is the idea of Hess's law that you learned in Chem 50. And if you remember Hess's law, everybody's favorite thing, that's pretty much where you take a whole bunch of individual reactions and kind of put them together to make an overall reaction. And when you do that, you can figure out the total energy that's associated with it. And a lot of reactions do sort of take place that way. Sometimes they're one step, two steps, three steps, four steps, a bunch of sort of steps. You know, for example, if we think about a reaction where it's A plus B goes to, you know, E plus F. And we may think about this as, oh, it just definitely just jumps right on over there. And it may not actually happen that way. It may happen in maybe a two-step process where maybe A and B make C and D, and then C and D go on and react to make E and F. And if you add both of these reactions together, and by the way, when you do add reactions together, everybody on the left-hand side stays on the left-hand side of the arrow. Everybody on the right-hand side of the arrow stays on the right-hand side of the arrow. Anything that's the same on opposite sides of the arrow can cancel or reduce. So in this case, we could cancel out the C since they're on opposite sides, cancel out the D that's on opposite sides. And here is our overall reaction, which is actually what we were looking for here. So reactions can occur in multiple steps. And when we can sort of display a possible way a reaction takes place, we could do that in what is known as a reaction mechanisms. And reaction mechanisms are, you know, sort of probable steps or possible ways that a reaction could occur. And they're based on a bunch of sort of individual steps along the way. And these are what are referred to as elementary steps or elementary reactions. So these are a series of sort of individual reactions that occur that when you add them all together gives you pretty much the overall reaction that you are actually looking for. And the sequence of all these sort of steps and the order at which it happens is what is known as the reaction mechanism. So elementary steps are individual steps that sort of lead to products being formed and the reaction happening. And the reaction mechanism is sort of the arrangement of these individual sort of steps along the way that is a possible explanation for how a reaction could take place. So for example, if we look at this reaction here, and when this reaction occurs or is taking place, you can see N2O2 being detected. But if you look in the overall reaction here, you do not see N2O2 anywhere to be found. And so if you were just solely looking at the overall reaction here, you would have no clue or no idea that N2O2 was actually made during this reaction, as it's not on the reactant side, it's not on the product side. So one way to sort of explain why this occurs, that we do see N2O2 when this reaction occurs, is through a reaction mechanism. And what that would imply is a couple of things: that somewhere in this mechanism, we do have to produce N2O2, which is why it can be detected as this reaction is taking place. But also, based on the overall reaction, we know that by the time the reaction is done, the N2O2 should also be gone. So it shouldn't be there anymore. And a possible explanation is here through two elementary steps. The first step, we see NO and NO coming together to make our NO2, which would account for why it is sort of found when this reaction is happening. But just as important, in the next step, we see that our N2O2 actually then gets used up. So we make that in an early step, we use it up in a later step, and that is, as we will talk about here in just a bit, that is what is known as an intermediate. And an intermediate is something that is made in an early step in a mechanism, but pretty much gets all used up by the time the reaction is over. And more importantly, it does not appear in the overall reaction for that system that you're looking at. So if we take both of these reactions and add them together, again, in this case, we can cancel out the N2O2, and it will leave us with the overall reaction that is happening here, which is our 2NO plus O2 goes to 2NO2. So this is an example of a sort of reaction mechanism. And again, here you can kind of see it visually. Our two NOs make our N2O2, which then gets used up to form our product. And just like in this sort of mechanism here, maybe a couple of steps, maybe more than two steps. It just really just sort of depends on the reaction you're looking at and the proposed mechanism. Now, as I mentioned before, when we look at a mechanism such as this, and we do see something like N2O2 that appears early on in the mechanism and gets used up by the time it's over, that is again what is referred to as an intermediate. And that's an important part. It's a substance or a species that gets made early in the reaction, gets completely used up in the end, but most importantly is not found in the overall reaction. So again, in this case, the N2O2 would be our intermediate. And when we look at these elementary steps, we can sort of describe these elementary steps in a couple different ways. Some are what are referred to as unimolecular, and uni meaning one. So it's basically an elementary step that has one molecule involved. It can be referred to as bimolecular, which basically bi means two here. So it's an elementary step that involves two molecules. It can be termolecular, which is an elementary step that involves three molecules. Probably not much more than that. Again, just logically think about reactions that you probably have seen over the years of your chemistry classes. You haven't really seen probably too many where there's like 4 or 5 reactants at a time happening, right? So usually most reactions involve like one reactant, some involve 2 reactants. Again, probably pretty crowded there would be something with 3 reactants. Again, we don't really get into much more than sort of that. In most cases, you don't usually have 5, 6 things sort of reacting at once in a reaction. So unimolecular, one molecule, bimolecular 2, and termolecular 3. If we look at each of these elementary steps, they are both bimolecular here. Again, 2 reactants and 2 reactants happening there in the second step. Now, what a reaction mechanism is really, when you sort of think about it, it's a sort of plausible explanation of sort of how a reaction may take place. Doesn't mean that 100% of the time, every single time, it sort of happens that way. It doesn't necessarily mean it. Um, it doesn't mean that there could not be a different way that the reaction could take place. But it is a lot of times when we think about mechanisms, sort of a plausible mechanism or way that a reaction can take place. And that's usually a very common sort of thing that you're actually trying to determine when you do mechanism type problems. A lot of times they ask you, is this a plausible mechanism for this reaction to take place? And your goal is to try to figure out, you know, based on what you see there, is it possible? Is this a possible way that this reaction could take place? Again, doesn't mean that it happens that way 100% of the time or always that way, but it's just a possible way to explain it. Now, something that is also a little bit different than what we normally do with things like rate laws and things like that is, if you remember throughout this entire chapter, when we write a rate law for a reaction, it is always found experimentally, which means we have values and numbers and all that kind of stuff. The one place where you can use the balanced equation to help you write the rate law is when you are doing reaction mechanisms. So this is really the only place that you could do that. And what I mean by that is, for every elementary step, you could write a rate law for it. So if you're given some elementary steps in a reaction mechanism, you can sort of safely write a rate law for that. And it is based on the coefficients that you see in the balance equation. So for example, here, if we look at this guy, we have A that goes to products. So the coefficient here is 1. So if we wanted to write the rate law for this first elementary step, it would be the rate is equal to K, A basically to the 1. And the 1 in this case would be the coefficient here. And again, this is the only place in kinetics where you're allowed to use the coefficient as sort of the exponent. If we had a bimolecular here, A plus B, again, the coefficient for each of these would be 1, which would give us a rate law for this particular elementary step, as the rate is equal to K times A to the 1 and B to the 1 in this particular case. And just like normal, you don't have to put the 1s in there, but that is sort of where it comes from. You could also have a bimolecular where we have A plus A. That's basically, if you add them together, 2A goes to products. And the 2 here translates into our rate law as the rate is equal to K A to the squared. So just to be clear, this is the only place where you can use the coefficient as the exponents. If it is not a mechanism problem, you need to figure it out the same way that we've been doing it throughout the rest of the chapter with the table, the rate 2 over rate 1 and all that. But here, specifically for elementary steps within a mechanism, it is allowed to use the coefficient as the exponent. Now, when you're asked, a question like, is this a sort of good or bad mechanism, for a lack of a better way of describing it, there's really two important things that has to happen for it to be a good mechanism or really a plausible mechanism. The first one's pretty simple. When you take all the individual elementary steps that they give you in this mechanism, and you add them all together and you get rid of all the intermediates that are present and whatever else that may cancel out or reduce, what you are left with is the actual overall reaction that you're looking for. So in typical these problems, if they're asking you to sort of prove this is a good or bad mechanism, they will give you the overall reaction that you're looking for. And the first sort of simple thing to make it a good mechanism would be, obviously, when you add up all the steps to that mechanism, you do get the overall reaction that we are looking for. Now, the second thing that has to happen in a problem where you're trying to figure out, is this good or bad in terms of the mechanism, is what is known as the rate determining step should have the same rate law as the one that's found experimentally. So a couple of things about that. First off, usually in these problems, or a lot of times in these sort of mechanism problems, they will give you the overall reaction that's happening, and they will give you sort of an experimental rate law. So they'll say, hey, the overall reaction is A plus B goes to the products, or C, the experimentally found or observed rate law was blah, blah, blah. And when you are given that experimentally found rate law in the problem, in order for this to be a really good mechanism, the rate law for the rate determining step needs to match it exactly. So it's got to be exactly the same for the step in the mechanism that is the rate determining step. You may be asking, what is the rate determining step? The rate determining step is sometimes abbreviated RDS for rate determining step. Very creative there. And basically, the rate determining step in a mechanism is the slowest step in that mechanism. So it's the slowest elementary step in the mechanism. And because it's basically the slowest step, it is the one that basically determines how fast that reaction can take place. It's kind of like when you're in the 10 items or less and the guy's got 400 items in front of you. Obviously you're not going to get through that checkout line until he gets through. He's your rate determining step. So that's sort of the same idea in a mechanism problem. There will be a step that is known as the RDS, or the rate determining step, and it is the one that basically determines how fast that reaction will occur. So there's really kind of two ways you could determine whether or not something is the rate determining step or not in a mechanism. The first way is sort of what we were just talking about, is if you're given the experimentally determined rate law and you write a rate law for one of the steps in the mechanisms and they match. So you got a step in the mechanism that has the exact same rate law as the one that's found experimentally. That would be your rate determining step, or your RDS. The second way, which is a little bit more difficult in terms of determining which one is the rate determining step, is they will give you the steps in the mechanism. And next to each step, they'll write like fast, they'll write slow. And I was just joking, it's not the hardest part. The one that's labeled slow in the mechanism is the rate determining step. So that's a much easier way to actually figure it out sometimes in these problems. And it really sort of depends on the type of mechanism problem you're dealing with as to sort of what information is given to you. But a lot of them will give you sort of all the individual steps, and really next to them, they'll say fast or they'll say slow. And there'll usually only be one that says slow. And that one is obviously your rate determining step, and the slow step in the mechanism, the one that will determine the rate law. That also means that the slow step in a mechanism like that, where they do label it slow, should end up with the same rate law as the one that's found experimentally if everything is good in terms of that mechanism. So let us take a look here. And that's sort of what we've been talking about here. Let's take a look here at this one. And why don't you take a second and see what you come up with. So here, the experimental rate law for this reaction was found to be the rate is equal to K NO2 squared. The reaction is believed to occur in two steps, which are listed there. So why don't you try to answer these questions for a couple of minutes, and then we'll talk about it. First off, what is the overall reaction here? What is the intermediates, or intermediate? And what can you say about the rates of step one versus step two? So take a couple of minutes and we'll talk about sort of what's going on in this type of mechanism problem. Okay, so since we're getting to the end here, let us take a look at what we got going on. So first one, pretty straightforward. We're looking for the overall reaction. So basically what we want to do is add both of these steps together. Again, whatever is the same on opposite sides of the arrow will cancel or reduce. So NO3 could go away, it looks like. We could also get rid of an NO2. And I think that should leave us. So that is going to leave us NO2, which is on the left-hand side of the arrow, CO, which is also on the left-hand side of the arrow. And on the right-hand side of the arrow, NO plus CO2. So this is the overall reaction that is taking place in this particular case. Now, what is the intermediate? So the intermediate in this case is the NO3. Now, is the NO2 an intermediate? Those are two things that we did cancel out. And the answer is no. The NO2 is not an intermediate because the NO2 is still there in the overall reaction. So although we did reduce it down, we didn't completely get rid of it. And remember that really the definition of an intermediate is something that's made early on in the mechanism and gets completely used up in the mechanism and is not present in the overall reaction. So in this particular case, although we did kind of cross out NO2, it is still there in the overall reaction, and that means it is not an intermediate. The only intermediate here would be the NO3. Any questions on that? Now, for each of these individual steps here, I'm just going to do that, I think, we can write a rate law. So we could write a rate law for step number 1. And again, because this is a mechanism and this is an elementary step, we could say that for step number 1, the rate is equal to K times NO2 squared. I got NO2 squared because if you combine this, that is 2NO2. Coefficient is a 2. That is where the 2 comes from here. And again, just a normal rate law. If we write the rate law for step number 2 here, and again, you could do this because this is a mechanism problem and this is an elementary step. The rate would equal K, and again, just our reactants involved in rate laws. So NO3 and CO. So if you remember that one important thing to determine, what's happening in terms of the rate and what determines the rate is this rate law right here. This was the one that was found experimentally. So the rate is equal to K NO2 squared experimental rate law. And if we take this rate law and we look at each of the steps, we see that step number 1 has a rate law that matches the experimentally found rate law exactly. And what that means is step number 1 is the rate determining step. It is the slow step in the mechanism. And what that tells us is step number 1 is going to be slow, and number 2 must be faster than step number 1, because again, step number 1 has a rate law that matches the one found experimentally. And what that means is that should be our rate determining step, or RDS, and that should be the slow step in the mechanism. So in terms of this mechanism, it's that first step that happens really slow, and then the second step happens faster. And because that first step happens slow, it is the one that truly determines how fast or slow this reaction does take place. Any questions on that? Okay, then we will stop lecturing there. We're almost done with the chapter. We got a couple more mechanism problems to do. We'll do that on Thursday, and then we will roll into chapter 13, which is equilibrium. Reminder that put that proctoral quiz up that you need to take by the end of the week again, so you could get yourself set up for when we use it for quiz and exams. and you shouldn't have any excuse. So make sure you take it. It is worth points. And if you don't take it and don't get the points and you can't get it working on an exam or quiz, you will not get any extra time or anything like that. So make sure you work it out now on this sort of practice one, just based on completion. And that way, when we take a real one, which is actually going to be next week, so next Tuesday, we will have a quiz on this chapter. So on chapter 12, it is, right? So on kinetics next Tuesday during, we might do it during lab, your lecture or lab. We will have a quiz on chapter 12 here. And so make sure you take care of the practice quiz so you'll be all ready to go for that quiz next Tuesday. Any questions on any of that? All right, so make sure you type here in the roll. If you didn't do so, I'll see everybody about 11:30. It's running a little bit long, so why don't we start about 11? Why don't we start about 11:40? Just give everybody a chance to get up and move around, since we're a little bit long here in lecture. I'll see everybody about 11:40 through the lab thing. Make sure again you put here if you haven't done so.